So after learning about the first crucial piece of calculus, limits, we now know how to look for the value at a point by approaching it with values that are very close to this actual value. And this leads us to another idea involving infinitesimals, which is one of the two main features of calculus. So, to start with the problem that plagued physicists and mathematicians in the 1700s, we'll look at a line like this. So, how can we find the slope of this line at this point? Well, it's pretty obvious. The slope of this line is just rise over run. So, delta y over delta x. And this is the formula for the average rate of change between 2 points, right? So, you're right, m, the slope, equals delta y over delta x, rise over run. That's pretty simple. But now imagine we had a graph that looked something like this. The graph of y equals x cubed. How can we find the slope of this? Because the slope of around here is basically 0. If we draw a line tangent to that, the slope around here is clearly very positive. So what's going on here? How can we actually find the slope at any given point here? So I'll remove these lines to make it easier to see. But this is a big problem in math. You need to be able to know how things change, which is the whole idea of calculus. So we can start by thinking of in terms of the average rate of change. So let's say we wanted to find the slope at x equals 2. How can we do that? Because the slope is changing as you go along the line, along the curve. So what we can do, we can make an approximation. Say we find the average rate of change between the point at x equals 1 and the point at x equals 3. So this is what we call a secant line. So this is a pretty good approximation, but it's not great because the tangent is a little steeper in reality. So I'll take these away again so you can see. But to find the average rate of change between 3 and 1 and find the slope of the secant line, we just use what we learned in algebra classes. We'll do delta y over delta x like we did before. So 3 cubed minus 1 cubed over 3 minus 1. And then that'll be 27 minus 1, which is 26, over 2. And 26 over 2 is 13. Now, that's just an approximation. That's not the actual slope of the line at this point. So, if we want to get really close to the actual slope, we can use a better approximation. Say we use 2.001 and 1.999. So then we can do 2.001 cubed minus 1.999 cubed divided by 2.001 minus 1.999. So when we do this, we get that the slope, which we'll label m for now, that'll change later, we get m equals 12.0000001. And the real value is actually just 12, but this is a very good approximation. However, it's a little annoying to calculate. You have to get out your calculator, and this is just not an efficient method for more complicated functions that are not just polynomials. So people like Newton wanted to find a way to make this very exact. So he started by writing out a general form of this average rate of change idea. So if we draw a graph of something that looks like this, then we want to find, let's just say again, the slope at x equals 2. We can define the average rate of change between 2 points. So this and a point over here. This is a secant line, remember. This is a poorly drawn line. So the slope of this we can get from, and let's call this little distance here, delta x. And this new y value up here, f of x plus delta x, which is just the y value delta x units away from 2, which is what we want. So the formula for the average rate of change between these 2 points will be f of x plus delta x minus f of x divided by x plus delta x minus x. And then if you notice, these x's just cancel, and we're left with just delta x at the bottom. So this is a general formula for the average rate of change between 2 points. But Newton wanted to make this an instantaneous rate of change, not just an approximation using the average rate of change. So what he did is he revolutionized math, and he made it so this was the limit as delta x approaches 0. So that means that this little delta x over here gets very close to 0. So if we redraw our graph down here so it's easier to see, that means that this delta x is getting really close to 0. So this is a better approximation than this point. It's a better approximation. And then as it approaches 0, as this delta x approaches 0, we approach the real value of the slope of this function at that point. So the general form of this is the limit as h approaches 0. H is just the same thing as delta x of f of x plus h minus f of x over h. And if we just plug in h equals 0, we'll get f of x minus f of x over 0, which is 0 over 0, and that doesn't work. So the limit, this limit is what we call the derivative. So we'll call this dy over dx, which I'll explain right now. This dy dx notation just symbolizes that, if we draw our line again, that if we have this point here, if we take a really, really small nudge to x, call it dx, which is the same as delta x, what's the resulting dy between these 2 points? Dy, the change in y, which is the same thing that we wrote up here, right? So this ratio is the same thing as rise over run. It's the slope of the line, but using very, very small nudges instead of like 1 or bigger changes. So using this nudge definition, you can plug in very, very small values like we did earlier, and you'll get really, really close to the real answer. And as you make h approach 0, you get really, really close to the real answer.